Last time we looked at solving recurrences, we looked at 3 types of recurrences. I will do a quick recap. Is this color okay, by the way, for people? If not, shout. This is divided by b. I can't write. So, all of the recurrences that we're going to look at today are going to follow this form. T of n equals a times T of n over b plus big O of f of n. This means this b controls the depth of the tree. This a controls the multiplicative factor, or the branching factor of the tree. And this says how much work is done on every level. There's going to be a theorem, Master's theorem, that's going to be incredibly useful in analyzing recurrences that follow exactly this format. Step 1 is going to be to compute n to the power of log base b of a. Compute. Step 2 is going to be to compute. Step 2 is you're going to take f of n, and then you're going to compare these two. If there's going to be 3 cases. If 1 is bigger than 2, okay, if one of these is bigger than the other, that's the answer. So if 1 is bigger than 2, the answer is 1. If 2 is bigger than 1, the answer is 2. And then otherwise, if they're on par with each other, if 1 equals 2, then you multiply your answer by log n. We'll see where this comes in handy later. In the interest of time, I'm going to move forward. So Professor Kani said he didn't get to teach Karatsuba's algorithm, so I'm going to try to teach that in 4 minutes, if I can do algebra. So the problem here is we want to multiply 2 numbers together. Let's take the numbers 122 times 14. This is too hard for me, so I'm going to erase this one. So what, 8, 2, is this right? I don't know grade school math. Yeah, okay, cool. If it's wrong, well, how many additions did I do in this operation? I had to add this and this, I had to add this and this, I had to add this and this. So overall, to multiply this whole thing, it took order n squared time, where n is the number of digits and operations that are like single-digit additions. N is not the amount of numbers. N refers to the digits. So I did this times this, this times this, this times this, this times this. So n refers to the number of digits. This took order n squared time. So if we count work we can count work different ways. We can count n to be the number of numbers we're multiplying, or we can count n to be the number of digits that we're working with. So here we're multiplying 2 n-digit numbers together, and naively it takes O of n squared time. So can we do it faster? So this guy who's dead now came up with this algorithm. y1 b times m plus y0. Great. So I want to multiply the numbers x and y together. You can think about this being equal to, in our case, this is 2, let's say if we wanted to write this as x, we can say that x is equal to 2 times 10 to the power of 1. And we can say y is equal to, y is equal to 1 times 10 to the power of 1 plus 4. So 2 times 10 to the power of 1 plus 2, these 2 coefficients match, these 2 coefficients match. So I did 4 multiplications here, and we want to know if I can do this faster. So let's multiply x and y together. What do we get? So x1 b to the m. Check my algebra, because otherwise this will make no sense. Okay. If we multiply these 2 together, what do we get? We get x1, y1, b to the 2m x1, y0, b to the m. Again, please check my math. X0, y1. Yeah, x0, y1, b to the n. Plus x0, y0. Okay, so if we look at this, we can kind of fuse coefficients together based off of similarities. So this is one set of coefficients. We can write b to the power of 0 here and say this is another set of coefficients. And then we can combine these. X1, y0 plus x0, y1. This whole thing is a set of coefficients for the term b of m. Okay, so we have one multiplication here. We have one multiplication here that we need to do. We have one multiplication here that we need to do. Right now, this is two different multiplications. So is there a way for us to reduce this down to fewer multiplications? Yeah, and I can't count either. This is two multiplications. This is one multiplication. This is one. This is two. Okay, so I'm just going to tell you that you can take you can take x. See, I want to subtract something. Okay, so I can do x1 plus x0 times y1 plus y0. And then I can subtract out. So this whole thing is equal to x1, y1, x1, y1, x1, y0, x0, y1, and then x0, y0. Okay, now let's take a look at these terms. We have x1, y0. Do we have that here? Yeah, we have it here. We have x0, y1. We have this here. Oh, would you look at that? We already computed this here, and then we already computed this here. So we can just subtract it out. All of this to say, I can compute this using 3 multiplications. Instead of 4. So I wanted to multiply two numbers together. I have this coefficient I need, I have this coefficient I need, I have this coefficient I need. Computing this coefficient requires 2 multiplications. I can reduce this to a single multiplication by computing this and subtracting out these two terms that I already computed here. TLDR, if we were to write a recurrence for this, T of n is the amount of time needed to multiply two n-digit numbers together. Does anyone have any idea what a recurrence for this might look like? That was algebra math. But to compute the product of two n-digit numbers, what am I doing? I will give you a hint. There's supposed to be some number here and then some number here, where I've put stars, plus. Okay, what should these stars be? Someone made a noise, hopefully. 3? Okay, great. Yeah, I agree 3, because I've taken the original multiplication and I've split it into 3 distinct multiplications. Okay, and then what should this star be? How many thingies am I multiplying at once? 2, great. Okay, and then the work that I'm doing is shifting over by m bits at most. So we can write this as O of n. So what is the solution to this recurrence? We follow the rule that we wrote over here. Compute n to the power of log base b of a. So n to the power of log base b of a The second step is we write f of n, which is big O of n. Step 1, step 2. N to the power of log base 3 of 2. Let's see, what is that going to be? Log base 3 of 0. Okay, 3 squared is 9, and then 3 to the power of 1. This is going to be some number between 1 and 2. So, does anyone have a calculator and can actually compute log base 3 of 2? It has to be something between 1 and 2. I'm going to guess 1.8. Oh, I was so off. It's 0.63. That doesn't make any sense. That means these two numbers are switched. What's log base 2 of 3?
1.58.
There we go. That makes much more sense. And that tracks because, here's why that makes more sense. Okay, cool. So what I'm doing is, I'm taking two numbers that are like two m digits, and I'm multiplying an m digit number and an m digit number. So the size of my number gets cut in half, and then I do 3 such products. So I know I'm rushing through this because I want to get to problems. If you followed none of this, all you need to know is naively multiplying two numbers takes O of n squared time for two n digit numbers. But with this new method, we can multiply two n digit numbers and n to the power of 1.58. I'm going to call it 1.6 time. So normally, n squared time. With this method, n to the 1.6 time to multiply two n digit numbers. Questions? So taking away from all of that, we have a faster algorithm that multiplies two m digit numbers. So two m digit numbers, or n digit numbers, in big O of m to the power of 1.6 time instead of n squared. Cool. With that, I'll start the lab. Describe an algorithm to compute the product of an n-digit number and an m-digit number. So we want to compute the product of, can you guys see the green or is it not visible? And m digit. Okay, so what this might look like is, oh, and then we're also told that n is bigger than m. This is problem 1. So let's say we take n equals to 3 and m equals 1. And this is our multiplication problem. So I have an n-digit number here, n is 3. I have an m-digit number here, m is 1. I'm taking the product of a 3-digit number and a 1-digit number. Using the fast multiply algorithm we just learned, what do you think a reasonable runtime would be if we just did this out for any arbitrary n m-digit number? O n squared, so that's naively, right? What about using this? Okay, so why is it n to the 1.6 instead of m to the 1.6? Yes, exactly. So essentially, if you want to use that algorithm, that's for two exactly n-digit numbers. What we do is we're going to zero pad the initial number to make it an n-digit number. So option 1 is going to be extend m to be of length n. So that means put zeros here. And then do the multiplication as if it was two n-digit numbers being multiplied, and you get big O of n to the power of 1.6. Okay, that's one option. The question is, can we do better? So again, we have an n-digit number that's bigger and an m-digit number that's smaller. Oh, did someone raise their hand? Okay. Yes? No? Like literal digits, yeah. This is a 4-digit number.
I was thinking it was binary. You had 3, 1.
No. It's like literal digits. Does this make you happier? Now it's two-ary. So the question is, can we do better? Oh, wait, actually, let me ask you this. What would it change if it was binary versus regular multiplication? I don't think it would change much. I think just your value of b switches from 2 to 10 in this paradigm. I think that's it. So what were you saying? Yeah, n-digit number times m-digit number. This is big n-digit. And then I have an m-digit number, which is small. And we want to multiply them together. So the lab tells us we should chunk the n-digit number into bits of smaller numbers. So we're going to take, this is of size m, this is of size m, this is of size m, this is of size m. And we're going to set n equal to 3m. Okay? Now that we have this, can we think of a faster way to multiply these two numbers together? Always go back to examples, and then always go back to degenerate cases. So let's take our single example from there. We took our example of 221 times 3. So if I were to multiply this out, I would take 3 times 1, or yeah, 3 times 1 times 10 to the power of 0, 3 times 1 times 10 to the power of 0, plus 3 times 2 times 10 squared, or 10 to the power of 1, plus 3 times 2 times 3 times 2 times 10 squared. So those are the 3 multiplications I do. So more abstractly, I need to multiply my m-digit number with an m-sized chunk of the top number. So this chunk times this chunk, this chunk times this one, this chunk times this chunk. Compute each of them. The only thing that changes is the bit shift on the power of 10. So what we see is the values closest to the left of the array need to be exponentiated a larger amount, and the values closer to the right of the array don't really need much exponentiation. Does that make sense so far? So we're here. Now we have the same problem. We have an n-digit number, so n digits. And we have an m-digit number here. So our algorithm can be, how do I want to index this? How are arrays usually indexed? 0, 1. Okay, I'll index it this way.
The solution was 1 dot dot n.
No, I don't look at the solutions. I don't like them because they're, well, for me, they're really confusing. Okay, so for I, we're going to start, I'm going to do 0 indexing because I think it makes the math a lot cleaner here. So this becomes, yeah, there we go. So for I okay, so I have an n-digit number and I have an m-digit number. How many different multiplications do I need to do? 3 in this case, or more generally for an arbitrary n and m. N, so I'm breaking n into chunks of m. Yes, there we go. At least you didn't say product. That would have been cool. Thank you. So I have this. For I in range this, so from 0 to n over m, I want to take the chunk of the top. So I'll say top chunk is going to be from index 0 to index m minus 1 from an iteration 1. In the next iteration, it's going to be from index m to 2m minus 1. So it's going to be from index we'll take the top number here, from index I times m to I times m plus m, which is I plus 1 times m. Let's check that out again. So on iteration 0, I go from 0 to m. On iteration 1, I go from m to 2m, roughly. I can put a minus 1 here. And then my bottom number is always just m, so my bottom number is m. We'll call this b. So now I need to multiply my top and bottom number. So how many digits is the top number right now? And how many digits is the bottom number? M, yes. For which one? Both? Great. So this is M.
0 to m minus 1 at the bottom.
Yeah, fine. You are right. Yeah, I think shit like this is why CrowdStrike happens. Anyways. So yeah, top times bottom. Okay. Oh wait, I didn't initialize a sum. So this is my P for my product. So I have some product stored here. In the first one, I can just take my product and add it to this. Okay, but what about in the second iteration? So by analogy, what we were doing is 2, 2, 2 times 3. What I just did was this 3 times this. And I said, hey, my product is 6. That's not right. I do. So if I start from, there's a reason I started on the right side, and you'll see that now. I started here. I have to shift this to the left by a certain number of units. If I had started my computation on this side, I get 6 here, and then I get another 6 here, but then I have to shift by m. And then I get another 6 here, but then I need to shift by 2m. So I'm doing extra work. I'm doing shift 0 plus shift m plus shift 2m. If instead I take the existing product that I have, I shift it by m one time, and then I add the new product on, what happens is, so the old paradigm was, hey, I'm going to take this, multiply it by this. I'm going to take this and multiply it by this, and then shift it by 1. And then I'm going to take this and multiply it by this and shift it by 2. So I've done an extra 1 plus 2 plus 3 work, which I'd like to avoid doing. So instead, I'm saying, hey, I'm going to start out my computation by taking the product of these two. So that's going to be 6. So that's my initial thing. And then on the next iteration, I'm going to do 6 times 10 plus another 6, which brings me to 66. And then I'm going to do 66 times 10 plus 6, which brings me to 666. So I just saved myself a bunch of needless shifts. If I didn't do it this way, I would need to manually shift each number. Okay. So, yeah. Right, so the reason for this is, so I could do 10 to the I, but then what I would need, I wouldn't need to, how do I say this? I could take the product itself. So if I were to put 10 to the, let me think. Here's why. Let's pick an example where we take 111 times 2. And let's trace through what happens here. So this algorithm says, take this product and this product. Good so far? So that becomes, my product right now is 2. Maybe I'll change this so it's a little bit more. Okay. Now that I have this product, in the next iteration of my algorithm, it says, hey, take the previous product that I have and multiply it by m. m is 1 in this case, right? So that says, okay, multiply this by 2 and make this equal to 20. Plus, I'm going to add on my top and bottom number, which is 4. So I get 24. So now, in the third iteration of my algorithm, it says, hey, take the 24 that I have and multiply it by 10. 240. And then add this 2 on. And then we get 242. The amount that you shift your previous answer by is agnostic of the index that you're on. Because I'm chunking by n, and my chunk size is fixed, where I am in the array has nothing to do at this fixed level of how much I shift by. If I had decided to iterate this way, then I would need to shift, this would not get shifted, this would need to get shifted by m, and this would need to get shifted by 2m, in which case I would matter. However, shifting takes time. It's not a free operation. So that would be an additional order 1 plus order m plus order 2m work added. If you do it this way, you're skipping all of that. Does that make sense? Great, runtime. How many iterations does this outer for loop take? This isn't a trick question either. Great, n over m. And then assume the splicing is order m work, right? I'm taking a chunk of m, so we'll say the splicing is order m work. How long does it take to multiply 2 m-digit numbers? Yes, great. This is m to the 1.6. And then this is another shift of just order m. Okay, so my total runtime here is going to be, for n over n times, the amount of work that I'm going to do is m to the 1.6 plus order m. If we multiply this out, what do we get? So this and this sort of can go away, because m to the 1.6 plus m is just big O of m to the 1.6. We multiply this out, and then we get n times m to the 1.6 minus 1, which is 0.6. And this is our final runtime, big O of nm. What did the problem ask for, runtime-wise? Yeah, that's exactly what it asked for. It asked for n to the power of log 3 minus 1 times n. Questions?